Okay, so if we have a big charge here and a bunch of small charges out here, all like charges, all positive charges, let's say. And the small charges are small enough that they don't affect each other. They're small enough and far enough away that they only exert a negligible force on one another. Then what's the direction of the force on each one? Well, it's repulsive, and people have no trouble drawing a picture that looks something like this. Okay, and then the lines of force you get from this charge should be parallel to these things that I drew, but I didn't do a good job of. It's kind of like this, right? Okay, and then in close to this charge, like the force is about this big. If you go out here, the forces might be much smaller. They fall off as a square of distance, and we're not going to worry about that at this point. But you get the idea. Okay. Well, is that divergent or rotational? Say that the field at that of this thing is diverging or rotating. Okay, so what we just did was here's a compass. North is this way. We put a current carrier under on top of this thing. Okay. And we saw that if we put the current carrier in this direction on top of the thing, we saw that if we run a current through the magnet needle of compass is a magnet. Okay. Needle of compass aligns this way, perpendicular to the current carrier. Okay. If we put the current carrier underneath, it aligns this way. Well, that leads us to the conclusion, at least tentatively, and of course, this bears out completely with any experiment that's ever been done, okay? That we get a magnetic field that surrounds the wire, looking at the wire end on, like this. So, is that an example of a field with a divergence or a curl? Well, it's obvious if you remember what we talked about with the examples that we did the first day. The first two examples were of a divergent field and a field with curl, I think. Okay? And when we did the direction fields for those things, we saw that. Okay, so hopefully you thought about that when you did the homework and drew your own direction fields. All right? And I hope you drew your own direction fields rather than just choosing the right one. The direction fields they showed you. You learned a lot by instruction. Okay. Well, the important thing is remember that if this is a vector field, field out, and this is a field G, then the divergence of L is non-zero. Okay. And the field G, curl of G is non-zero. What do you think the curl of this one would be? What would the curl of F be? No rotation is apparent. We suspect curl of F might be zero. It should be right over here. So we're going to prove it. Okay. Over here. So we pose the question, is the divergence of G zero? Okay. Okay, well, let's go back to the definition of a conservative vector. Okay. Now, what's a conservative vector field? Okay, so we can recall that for conservative field, it's equal to gradient of F for some potential function F. And that should be, you just did homework assignment for a reason. And the integral of F dot ds is path independent. Now, you knew that when you did the integrals because you just used the endpoints, you found the potential function, you just used the endpoints, right? Evaluate the integral, but did you really see that in the context of conservative field? Did that help you get a bigger picture of what a conservative field is? Okay, or are you just focused on here's how to get the answer? No, nothing wrong with being focused on here's how to get the answer, but try to think, where does this fit into a broad scheme? We're talking about conservative fields. Okay, so put that together because as soon as you see conservative field, you think it's a gradient potential function, which I got from somebody right away. Didn't really get the path independence. Okay, those are the two really important ideas that we're going to need in that sequence, and you're going to need in your field. Okay, if you especially if you go into like electrical or mechanical or civil. Okay, and most other engineering disciplines. I'll make use of this. Okay. Okay, so let's just pick on this part of it for right now. Okay, so that is conservative. Del F. Great investment. We're talking about the called the potential. What is curl balance? Well, the curl is del cross F. Which is del cross del F, right? Well, right on. What do we mean by del cross del F? Okay, now again, I'm not getting on your being certain or anything, just pointing out, if you don't know what del is, then you haven't been paying attention to the right way. Okay? Because you have to know what del is when you take the exam. I'll tell you what del is. Now, it could be written as cylindrical or spherical coordinates, but you really don't want to go there. Okay? Now, I hope that's really, really familiar, and you're sitting there thinking, oh, how did I not know that? Okay? Well, think about how you not know that, and think about how you're approaching this course. If you're missing stuff like this, then you're not locking stuff in that you're going to need, okay? The results on the test weren't terrible. Everybody passed. Had a couple of B's. but you know, you're on a capable base. You might not have time to make A's. Your life could interfere with your ability to put all the time you need to put into the course. But when you don't know stuff like that, and this after doing a couple of sections where you needed to use it, you're not locking in, you're not identifying the things that you need to know. Okay? So another way of saying that is, hey, you need to know that and you need to know this. And it's not hard to know that because you've done all kinds of stuff, but maybe you're not writing things out. Okay? And I think you probably are because most of you wrote things out pretty well on the test. Okay? Doesn't mean what you wrote is right in every case. Everybody made mistakes. But I see evidence that you know how to write things out. But make sure that you are, because that reinforces what you're doing. If you've written out the Dell operator a dozen times, which you should have in doing these problems, you would know right now what it is, and you'd be able to prove that this is zero. Okay? Okay, now, given that this is Dell operator, can you write out this expression? All right. Well, I want to work from the inside out. Dell out is this. Okay. So everyone wants to write the determinant, and that's appropriate in this case because you got three components here, three components of the Dell operator. You're probably going to want to use the determinant. And I would use the determinant, even though I like the distributive law. I'm sorry. Okay, a lot of people got down to here and didn't know what to write here because they never wrote this out. Okay, so you do want to write that out. And you can have partial depth with respect to x, partial depth with respect to y, partial depth with respect to z. And you work it out on your own. And you really need to do that. It's one of those things that can heighten probability. They don't turn out on a test. Okay? And you want to convince yourself of itself. I mean, it just comes down to partial respect to y, partial respect to z, minus partial respect to z, partial respect to y. So you just write it out. Okay? You know, this minus this minus this. And I do it by minors, incidentally, since most of you are either in or had linear algebra. How you're going to extend things to higher dimensions. If you got to write out two new rows and just do diagonals, okay? That's handy. I don't object to it as long as you do by minors. You know what I mean, right? Everybody's expanded determinants of linear algebra. And you know, if you get to 4x4, that was tricky to use by writing out a couple of rows here and diagonal lines. Handy. I used it. Okay. I probably used it before I knew how to do minors. Okay. But make sure you do minors. Okay, well, this linear algebra is foundational for a lot of engineering matters, calculus. Okay. Well, the other thing you can see is that if the curl isn't zero, then the thing is not conservative. Okay, it's an if and only if proposition. You should read that proof. You should understand it. After doing this, it should be easy to understand. All right. Also, what about the divergence of the curve? Curve G. Etc. Write it out and do it. Okay. If X, Y, Z equals this. Calculate quickly. Yeah, start by writing out the del operator and a dot. Gotta urge you to write these things out completely. Some people want directly to the solution. That's right. Because they had it written out someplace, looked at it, wrote down the right thing, and thought that they learned it. Okay. No, don't work from something that's been written out before. Write out your solutions. Okay. I swear if you'd have been taking 5% more time to write things out completely and construct a solution that somebody could follow, including you if you're reviewing, I think everybody would have made at least a letter grade higher on the test, or maybe higher than that. Okay. So I'm just saying, okay, divergence of F is del F, which equals partial with respect to x I plus partial with respect to y j plus partial with respect to z k of dotted with x squared. Uh-oh. Okay. Having a moment here. Have been since I woke up 2 hours late, 2 minutes before my first class to take was to admit. Wrote down something. That doesn't make sense. Del F doesn't make sense. Del dot F does. That's not what I intended to ask. Sorry. Didn't want to put that dot in there. I realized I needed it to make sense of my expression. But having written the thing out, another advantage of writing things out is if you do something boneheaded, something's probably not going to be right in your solution, which should tip you off. What I want on here is x squared plus y squared plus z squared. Put the I, J, and K on it. Okay. Divergence of F equals del F, which is this operator applied to x squared plus y squared plus z squared, which equals partial respect to x, I, well, partial of this with respect to x is just 2x. Partial of this function with respect to y, well, derivative of x is 0, derivative of z is 0, derivative of y squared with respect to y is 2y. And that's pretty much all you have, okay? Now I could go on and ask, okay, do the curl on this. Yeah, it doesn't hurt to just write it out. It just takes maybe a minute or two to write out what the curl of this is, and you would find that it's 0. And this is not the divergence. Now, what I wanted was the divergence of del F. Well, I've calculated here now is del F equals this. So del dot del F is, well, we write it out, partial respect to x I plus partial respect to y, okay, plus partial respect to z, okay, of 2xi plus 2yj plus 2zk equals, and what have you said is the result 6. Well, what I was thinking was not, well, I said, because let's look at this. This is what we get. This is del F. And now we have del dot del F. Each of these partial derivatives is 2. Okay. So if you thought it was 6, you were right, and you probably understood all of the details. Okay. Now I'm illustrating here. You want to write it out. Also, it helps if you have a problem that's properly posed, which it wasn't. That was my fault. Okay. Let's curl this function, or it's trying to trick me. Okay. What's the curl of this? It's just del cross. That means ijk partial with respect to x, partial with respect to y, partial with respect to z, 2xy, x squared y, xy squared. Now, I don't have any z dependence in this, so it's going to be fairly easy to do this. And I could have actually done this using distributive law. I think you probably ought to think about how that would be done. Still, here it is. Okay. And this equals what? It's I times the first minor, which is this, minus this, times 2xy minus 0. Okay, because it's I times the determinant of this matrix, right? And then I'm going to write it out as I would with minors. and use some tricks. Although the trick is fun. Okay, the minor we get when we eliminate J, and it's not plus minus. I mean, you got linear algebra, you know what else. I'll have to go back and write up. Okay, so I've got what matrix? Let's I got this column and this column. Okay, and you're going to have the partial with respect to x of x y squared, which is going to be y squared, and the partial with respect to z of 2xy, which is 0. And then it's plus k times the minor that we get moves underneath that column. Partial with this respect to x is 2xy, and the partial of 2xy with respect to y is 2x. So we get 2xy plus, no, minus y squared j plus 2x times y minus 1 k, choosing the fact. Okay. Well, this tells me two things. One conclusion is let me write out, never use, I never gave the field a name. So I'm saying now it's curl F equals this, so F is this function. I can say this field ain't conservative. Okay. Also, divergence of F, which is what? Well, you can write it out, but the x derivative of this is 2x. Derivative of this with respect to y is x squared. Derivative of this with respect to z is 0. Well, actually, if you read it, this means that F isn't the curl of some other field. Now, I'm going to digress just briefly to some electromagnetism. Okay, just very briefly. Remember that electric fields are conservative. E is an electric field. some potential function B. We call the potential function B here your electric potential function, measure and voltage. Okay. Now, depending what kind of engineering you're going into, I know at least one of you is going to do electrical. I'm curious. I'm not sure. Okay. So electric field's conservative and so forth. Okay. Magnetic fields used generally be to represent a magnetic field. All right. V is a scalar potential. Just some function has a number for every point of space. Okay. A is a vector function. So what we call V a scalar potential, A is a vector potential. Okay. Now it's just worth the logical relationship between this statement and this statement, whether you know anything about electricity and magnetism or not, to kind of understand why we call this a vector potential and this a scalar potential. Okay. Electric fields being conservative, we can always find your scalar potential function by integrating your electric field. Finding a vector potential function a little more complex, but not beyond what you might do or what you might see in some of the discussion text. But you're probably not going to see either of these things in the problem set. And I'm not going to put anything that requires that you understand what I just wrote there, okay, on an exam. Although I might well say, okay, here's what a vector potential function is. Here's your electric field. Find out the vector potential difference between this point and this point. What's the difference in the value of the vector potential function between this point and this point, which just means you do the simplest line integral you can from this point to this point. So everybody's going to remember that, right? No, I'd give you plenty of explanation, but it would be in the context of this course, okay? Or maybe I just give you a function and say, okay, how much does what's the integral of your electric field between these 2 points? And then I'll say, now what you just found is the difference in voltage, without you having to interpret that, without you having to do anything with it, okay? And I don't want to throw something at you that's completely off the wall. Okay. Okay, what surface do you get from this? For you, Well, I'm not gonna ask you to do anything. We've got like 2 minutes left. In the XY plane, unit circle, x equals cosine of u. U from 0 to pi. Now that should be completely clear to you. A lot of things we've done, okay? A lot of things that you've seen. If it isn't, make sure you understand it thoroughly, okay? Well, this means that x equals b cosine u, x equals b sine u. It's just a set of circles of radius d. So let's say that this is b equals 1, this is b equals 3/4, this is b equals 1/2, and this is b equals 1/4. Okay, if the unit circle is this, then if I multiply both x and y by b, it's going to make the circle bigger or smaller depending what b is. If b is 1/2, you're going to have a circle of radius 1/2. If b is 2, you're going to have a circle of radius 2. And if b is a continuous variable that goes from 0 to 4, you have a disk that goes from the origin, spreads out to a radius of 4. Does that make sense? So that this gives you a disk of radius 4. Okay. Now, z is equal to b. Well, that means above each disk, disk of radius b, we come up b units. So let's see, this dimension here is b. So we come up b units in the z direction, which gives us a disk up here. Now that's starting to make you think of the cylinder, but we don't have a cylinder. Okay. All we've got is this circle above this disk. Okay. Now, if we go to a different b, a bigger circle, then we're going to get a higher circle, a bigger radius. And what you're going to end up with is like a cone. Radius 4 and altitude. Okay, kind of sloppily drawn. You should ponder this and understand this. Put numbers in if you need to convince yourself. But it comes down to this gives you a unit circle. If I put a b in front of it, it gives me a circle radius b. If I raise it up 4 units, that circle goes up here, but nothing between here and here is part of your surface. It just gives you the surface of this cone. Okay. Now there are other surface hemispheres, paraboloids, and all kinds of things. You're going to have to be able to parameterize those to do stuff that we're going to see in the rest of the course. So review parameterization and make sure you understand that. And if you don't, tell me what you don't understand, email me or whatever, because I want you to have that as clear as possible when you start next week. I would also read ahead because things get very challenging. Okay. if you don't understand the basics.